Tom. And if he doesn't mind an overused cliche, he's one of the rock stars of our field. He's uncommonly broad, combining both theory and practice, and is still having stellar careers, both in academia at MIT and in industry. He received his bachelor's in electrical engineering and computer science from Princeton and his PhD in mathematics from MIT in 1981. He's professor of applied math, and he has headed the algorithms group in Computer Science and Artificial Intelligence Lab, CSAIL, as it is more commonly known, at MIT since 1996. In 1998, he co-founded Akamai Technologies, where he's currently the CEO and a member of the board of directors. We all know how important Akamai is in our modern cloud computing ecosystem. Professor Leighton is an eminent authority on algorithms for network applications and has published over 100 papers on algorithms, cryptography, parallel architectures, distributed computing, combinatorial optimization, and graph theory, and has produced 2 well-known books, including a leading text on parallel algorithms and architectures. He holds numerous patents involving content delivery, internet protocols, algorithms for networks, cryptography, and DRM. Among his many awards are the IEEE Babbage Award, and he's a fellow of the Academy of Arts and Sciences and SIAM, as well as a member of both the National Academy of Engineering and the National Academy of Science. Again, it's a great pleasure to welcome him here.
Thank you very much. It's really nice to be back with longtime friends and have a chance to talk with you all today. My talk will not be about theory today. It'll be about some of the big challenges that the internet is facing. And they are technology challenges, engineering challenges, systems challenges, and business challenges to solve them. I'm going to start with a video that sort of chronicles the tremendous progress that's been made in the internet to sort of put things in context. So if we could get that to go.
I wonder though what sort of a life would it be like in social terms? I mean, if our whole life is built around the computer, do we become a computer-dependent society?
He will have in his own house, not a computer as big as this, but at least a console through which he can talk to his friendly local computer and get all the information he needs for his everyday life, like his bank statements, his theater reservations, all the information you need in the course of living in a complex modern society.
a lifeline when it comes. Every second's a lifetime, every step is a mile, every heart beats a lifeline when it comes. Every moment's forever.
You know, it is really amazing, how much has changed. Some of us here, like me, are old enough to remember a world where none of that existed. And a lot of you are young enough to have never known any other world than what we have today, and probably imagine it just was always that way. I think the most amazing part is, as much as things have changed, we're just at the beginning as to what's going to happen. A lot of people talk about the world now. They give it the name of the Internet of Things, the Internet of Everything, the hyper-connected world. And whatever you call it, basically it means that everyone and everything is getting connected. And that's billions of people, tens of billions of devices, and countless petabytes of data. And the expectation is that it's all going to just have instant access and be intelligent, and whatever you want is just going to be there. And that creates some enormous expectations, really, for technology and for business. And today I want to talk about, 4 grand challenges. And these are the grand challenges we're working on at Akamai. I think they are perfect challenges for the major universities, to be working on, because they're rooted in technology. And I'll talk about each one in some detail, and that's what the focus of my talk will be on. The first is creating a world where everybody, or billions of people, can go home at night and during prime time watch a high-quality video, TV show or sporting event, online over IP. All right? That is not possible today. We're not even close, and yet this year you're going to hear a lot of buzz about broadcast TV moving online, cutting the cord, cutting the cable. There's going to be some very attractive packages that are going to be announced over the course of the year that will induce a lot of people to switch their broadcast TV watching to the Internet. And we'll talk about some of the challenges there. The second is, how do you make a world so that when you click on that new device you bought 6 months ago, it's instant response? The funny thing is that, you get that new device, it's very cool, and it's the new technology. You think it should work better than that clunky thing on your desk. And it doesn't. And it's not going to. And that's a frustration. It should be instant. Well, how do you make that happen? The third is that everything is online now. Everything. The government, the defense, companies, banking, everything about you is online. And it's totally insecure. How do we make a world where all the web and the Internet can be secured? And then the last is, companies, enterprises now have everything online. Their applications are moving to the cloud. Their employees want to access the company applications using their latest cellular device. How do you make the company networks work? Now, a lot of you don't worry about that too much. A lot of you are in academics, and you don't even interface with that. But for companies, this is a big deal. How do you make enterprise networks be fast, reliable, affordable, and secure? Okay, so let's talk about video. That's getting to be a pretty big deal out there. Already, even though very little video is watched online, the traffic is growing at an enormous rate. And these are just 2 examples of major events, like the Winter Olympics and most recently the World Cup. And they're growing. The traffic used for an event is growing annually at over 60%. And we haven't hit the inflection point yet in the curve. All right, so it's doing 60% a year, and it's going to explode from there. If we look on the Akamai platform, and we deliver a lot of video. We do pretty much all the sporting events, and most everything except for YouTube and Netflix, which are both huge. Pretty much most of the rest Akamai will deliver. Traffic on our platform is growing at more than 60% a year. And so last year we peaked at 26 trillion bits per second. That's a lot of volume. And you can see the graph there, and you say, well, where does this go? It's a question I have to worry about, because I've got to build out the infrastructure to support this. And so let's try to do some math to see what might happen on the internet. Suppose that the world has 2.5 billion people that want to go home at night in prime time and watch a high-quality video online. Now, there are already more than 2.5 billion people who have watched a video on the internet. But that's different. It might be a YouTube short-form video. That's different than going home at night and watching your favorite TV show, online. And suppose you want to have it be at decent quality. All right, now, for comparison here, standard def TV, which already isn't good enough anymore, that's about 1 to 2 million bits per second, 1 to 2 megabits per second to get standard def TV quality. If you want to do DVD, not Blu-ray, DVD, that's 4 to 5 megabits a second. HD is an abused term, so I won't even go there. But if you want Blu-ray, 20 to 40 megabits a second. 4K is the new format. Most of us don't have the 4K TVs yet, but they're starting to come down in price. I wouldn't be surprised that 1 or 2 of the people here has a 4K TV. The content is starting to come online in 4K. 4K is 32 megabits a second. Now, people compress it, and if you compress it down to 8 million bits a second, it looks terrible. So what's the point of having 4K? 16 megabits a second, if your TV is not too big, is okay. Maybe tricky there on a size like that if you're up close to that. All right, so that's how many bits per second in terms of where we are on the quality curve. 8K is going to come next, and that's more than double. And even at 4K, you're still doing 32 frames a second, and that's not good enough. Humans, when you're watching a sporting event, as the camera pans, it jerks, okay? And so you really need at least double the frames per second. So the complexity in terms of how many bits per second you need to send to the viewer, you want to be thinking of tens of megabits a second as to where we're going, all right? Tens of millions of bits. I'm assuming just 10 here, all right? So more the old formats. How much traffic would that be? If you're it will. That's a great point. So maybe you could leverage it across time zones. If you were serving it from here, say the hub was in Providence, well, you could use the same capacity to serve it at prime time here as prime time in the West Coast, prime time in Tokyo. The problem with that is you can't get the throughput, and it'll just crush everything. So in fact, you're going to have it be local to do this, but that's a great, great point. So literally, you do want to do the multiplication. That's 25,000 terabits a second. All right, so that's 1,000 times where we are right now, basically. 1,000 times Akamai, 1,000, within close to 3 orders of magnitude for the internet to do that. That's a lot. All right, so now the question is, well, okay, is the capacity there? We look at that and say, oh my goodness, if you plot 25,000 terabits a second against what we're doing, you can't. You even take the log plot, it's concerning. All right. People are starting, I remember it was like 15 years ago. Who was it that said video is going to break the internet? That was 15 or 20 years ago? Yeah. I'm not saying that. I'm asking the question. All right? And they had to eat some document, I think. Who was it that did that? Somebody famous said the video is going to break the internet.
They're not also watching something else at the same time, right?
Well, that's the next thing, is there's lots of people. Yeah, you have multiple devices. There's different viewing formats that even had more traffic. All right, so this is a big deal. So let's look at the internet and see where the capacity is or isn't. Now, what people immediately think is, well, wait a minute, the connections to the homes are the bottleneck. And 15 years ago, it was. Your dial-up modem, forget it. You're not going to watch any quality video. Today, actually, we're pretty close to the capacity you need. And this I'm sure is wrong by a factor of 2. You know, there's no real accurate estimates, but more or less, there's, say, 400 million lines into homes and offices and schools. And the connectivity in a lot of the world is very good. You know, there's whole countries that are connected at over 100 megabits a second, some with gig links, a gigabit a second into the homes. But say you have about 400 million connections in the last mile to the homes, and at an average of 25 megabits a second, that's 10,000 terabits a second. Yeah.
Where are you? What scale is this 400? Because just in the U.S.
World. No, you don't have it in the U.S.
Well, no, because
Global.
between offices and homes, the U.S. itself, I can imagine it's 100.
Yeah, probably 100 million in the U.S. Yeah. But this is global, okay? And of course, most of the population is outside the U.S. And the U.S. is not a leading country in terms of last mile connectivity. There's many other countries ahead of the U.S. So, okay, so this is not so far off. This is not the bottleneck, all right? A lot of you have FiOS, for example, or you got something, you know, in your homes that are probably you bought it, it was advertised at 40 megabits a second or 100 megabits a second. All right, so that's not the problem. Things are good there. The problem is in the core, and you can look at that in two ways. The cloud data centers. People talk about the cloud. There's, you know, maybe a few hundred data centers, or the big tier one backbones, AT&T, Sprint, you know, Verizon, and there's maybe a couple dozen of those guys globally. But either way you do the math, it comes out about the same. Say there's 100 major networks. They're not 100. There's 10,000 networks, but there's less than 100 of the big tier one backbones. And say they had a backbone capacity of 5 terabits a second. They don't. They're not even close to that. But give them credit for growing and technology innovation and so forth. Do the math. 500 terabits a second with growth. Now, this isn't too hard for this group. You know, do that math. A tiny fraction of what we need, even if I'm wrong by a factor of 2 here and there, we're not close. So the notion, which everybody has, that we're going to deliver this video over the internet online, and there's going to be a video server that delivers you the stream for whatever you want to watch, and then you're going to get it in your home, and it's going to come from the cloud? Not going to happen. Just won't. And you already see the problem. You know, you think about it like net neutrality, people following what's going on there with the FCC and all, and you see the complaints, you know, a company like Netflix will complain, hey, that big bad carrier is thinning my streams, and so the viewer can't get the good quality movie. I don't know if they are or they aren't, but there's a technology reason why you're not going to get a good quality movie because of this problem. It's clogged coming to the choke points, getting into the network and the peering point, getting out of the data center. It's clogged. And
You're telling us that video will break the internet.
I didn't say that, but we got a big challenge here. The capacity's not there, and with the existing way people are doing things, you know, not gonna be there. Yeah.
But a lot of this is it's read-only data, and there's a lot of sharing, right? So,
Yes.
So your numbers are sort of not counting for that.
So let me get to that, because that's going to help some. Yeah. All right. So let me talk about what Akamai does, because we started the company to do this. Yes. All right, and even we're going to get behind, but this is why we started the company. So our approach is don't serve stuff from cloud data centers, because it's not going to scale. You can't keep doing it. And so we deploy our servers, our computers, everywhere we can. We're probably on the Brown campus network, I'm guessing. You know, we're on, anywhere we can go, we deploy our servers. They're in thousands of locations, close to the end users, because it's, you're right, a lot of people are watching the same movie or the same TV show or the same sporting event, and if we can deliver it closer to the end user, well, we know there's more capacity as you get farther out towards the users, and so you're less bottlenecked. If you try to distribute it from the core, you're going to be choked, and that's what happens with things like Netflix that do that. All right, now, if you can be distributed like this, and this was the thesis for creating Akamai, well, the content you want is nearby. Maybe it's cached if it's cacheable, and you get it fast, and you got capacity. Now, sometimes the content you want is not cacheable. It's your bank balance. You're buying something at Amazon, you know, or eBay, and they've got your credit card, and they're trying to protect it, so they got it in some vault in their data center. And that's okay, so we got to get back to that vault, you know, and so we had to build our own virtual internet. We use our own routing protocols. We use our own communication protocols. We use our own application layer enhancements. Now, the protocols that were used to create the internet were amazing in how good they were, how much they've allowed the internet to grow. TCP is great. You can do better. BGP as a first pass was great. Not so good that it ignores congestion. That's not such a good thing about BGP, but you can do better. Now, the problem is you can't just rebuild the internet. You can't. You got all these standards bodies, you got all these governments, and you just can't drive things through. So the way to do it is you build on top of it, and that's what industry can do. And so that's what Akamai does. We built our own virtual internet, as if you all were designing a new internet yourselves. You do it a lot smarter now, even though what they did way back when was awesome. And so we can get back to that data center to get your credit card and do your transaction really fast. Even though maybe nothing is cacheable, it's a lot faster and more reliable. Now, as we look towards the future, even this is not going to be good enough for you all to go home at night and watch broadcast TV over the internet. And this year, people that you know and love are going to try to sell you packages to do that. So to make it go even farther, you got to use new technologies, well, old technologies in some sense, like multicast, which never has worked in the real internet, but you got to make it work. You got to pre-position content. You got to have peer-assisted delivery, peer-to-peer, but not in the wild. You got to have really highly controlled and highly secured peer-to-peer. To really make this work, we want a device in your garage that you don't even know about and don't care about. It's always on, always connected. Maybe it's your cable modem. Maybe it's your set-top box. Maybe it's your smart home gateway. It's got storage, which is really cheap now, and it's got our software on it. So we can do multicast to it. We can pre-position content, and we can treat the entire neighborhood like a cache. Okay, so that we're going to try to guess what movie you want to watch tonight and get it there ahead of time. We're going to be wrong sometimes, but maybe we have it on your neighbor's device, and we're just seamlessly going to move it and get it to work for you. That allows you to take advantage of all the capacity out there that you have in the last mile in the homes, allows us to take advantage of all the power you're already using, all the CPU that's already in a box in your home. You already got the CPU needed for this. And so there's no additional cost, and allows it to scale. Because there's no way in the world there's enough power or dollars to do it in the cloud data centers. And this is a hard business problem. Aside from the technology, making the technology to make this work, there's the business problem that we're facing is how do we get our software onto those devices in every home? That's expensive real estate to be able to get there. And then to make all this work. Because the content guys, you say peer-to-peer, the content guys break out in a rash. The broadcasters. That's a horrible thing. That's BitTorrent, And the carriers, they hate it, because they think that it's going to cost them a lot of money, right? And they're already in the net neutrality wars, over what's going on. So the carriers hate the content guys. So it's really a complicated business landscape now. So it's technology and engineering, married with business to solve these problems. Okay, so let me switch gears and talk about, yeah, sure.
Sir, the machine in my home
Yeah,
will have copies of the movie that I didn't purchase.
correct. And you wouldn't even know it's there. And it wouldn't have the whole movie. It would have chunks of it.
And the movie industry is going to be happy with that.
Well, this is a challenge. And so we invented other names. Like when I'm with the movie execs, I call it client-assisted delivery. I do not use the word peer anywhere. Right? They go, they turn red, and it's bad. But it's the only way this is going to work. And they do want it cheaper. They do want to have security or digital rights management around it. And you need it cheaper, and you need to scale.
And in theory, I can figure out what movies my neighbors are watching.
No, you can't, because it's all going to be encrypted. You're not even going to know what chunks you have on your device.
Potentially learn by how quickly it's delivered that someone in your neighborhood has cached a given movie?
It'll always be fast, and we'll always have parts of it. The control will always be in our servers. You will never be able to reconstruct the movie from what's in the neighborhood without the piece we have and the keys we have.
Boy, what a
Yeah. You know, no, this is hard. And you know, you talk to the carrier execs. You know, because I come from the technology side, and it's odd for somebody with my background to, you know, be a CEO or, you know, be doing this stuff. But you know, you meet the other CEOs, and you ask them, okay, well, how do you think you're going to be delivering broadcast TV over the internet, you know, with high quality at scale? And they say, oh, that's easy. It comes from the cloud. You know, it's like, well, have you done the math? You know, it's hard. So there is sometimes a disconnect. Yeah.
How would you take this approach to deliver live TV, though? Like a live broadcast?
Live broadcast you can't pre-position. The nice thing about live is there's only a few thousand channels. Okay, there's not millions of channels. And you do multicast, absolutely, yeah. And now multicast is a technology been around 30 years, never successfully deployed on the internet. The routers are enabled for a flavor of multicast. You know, we have to get our communication stack into the home to enable it. And the carrier's got to do an upgrade on the software in the router to turn it on. Or they got to do a hardware upgrade, which is, forget it, that's off the table. But the software, we got to get them to turn it on. That's really been hard. You know, we can get to the trial stage, but I figured to turn on multicast in any scale is probably at least 5 years away, because the carriers move very slowly with that kind of thing. And then there's one carrier that actually turned it on in Asia, and then they thought, wow, they've gone to all this effort to turn it on. They wanted to charge five times as much. And the whole point is it should be 5 times less. You know, so it's a non-starter when you do it that way. Okay, so that's a big, big problem. And there's work that needs to be done, starting with academics and algorithms, all the way through the business implementation and deployment and engineering. The second problem, also very hard, is you'd like that device, you just bought this cool new thing, you want to click, and it should be there. All right? And oddly enough, it's getting slower. Now, this is weird for technology. Technology is always supposed to be faster, better, cheaper. And there's a reason it's getting slower. If you look at a typical page size that you want to download, it's doubled in its weight because people are making their pages have more stuff, cool animations, graphics, software on them, JavaScripts on them. So the number of bits that have to be delivered to your device to make the page display has doubled in 2 years. And so if you think about a fixed bit rate to your device, that means it's going to be twice as slow. You got more objects on a typical page. Every object, the way the browsers work, is you got to go fetch it. And you can fetch a few at a time. That makes it harder. More and more of the usage is on mobile devices and on cellular devices. And cellular is a nightmare. All right? That, you know, just to connect from here to the tower, you know, down the street, on cellular, the latency is like going from here to Romania on the landline. Now, if you knew you were going to Romania, you'd say, okay, I get that it's slow. Going to the tower shouldn't be that way. And on top of it, the protocols in cellular, very chatty. Lots of back and forth, you know, communicating. Every one of those taking a large latency. Now, that means that unassisted page load times are getting longer. Now, the cellular problem is not going to go away. And that's because the infrastructure was built for voice. Voice is 8,000 to 16,000 bits per second to do a decent voice phone call. But now you think you're going to watch video on that device. You're going to watch a sporting event. And you're not going to be happy unless it's at least a megabit a second. And you want to download that page, which is over a megabyte, to come in a second. That's 8 million bits a second. That's 1,000 times voice per second. And that's a big problem. The infrastructure is sort of stuck there. Now, yeah, we're going from 3G to 4G. In some number of years, 4G will be a large percentage. 4G is great when you're the first one. You can get up to 100 meg and the latency is lower. Aggregate capacity on 4G, around a factor of 2 more than 3G. We need a factor of 1,000. 5G, a little bit better when we get there. But nowhere near what we need. So you got a technology problem there. How do you make it seem fast? Now, speed matters. I mean, you all know this, but you know, every commerce site has done this study where the blue bars are the histogram of how long it takes real users to download a page on their site. And you see that maybe the average is around 4 or 5 seconds. And this includes landline, which is much faster. And you got a bunch of people out there at 11 seconds, which is just the dead zone. If it takes you 11 seconds to download a page, you do not buy. Virtually certain you do not buy. Now, the orange line there, that's the conversion rate. That says, okay, you downloaded the page, what are the chances you bought when you were there? And you can see that as it gets slower, you buy less. And if you can be under a second, you buy a lot. Now, partly that's because you could do it faster, but partly it satisfied your need for speed and you go and do it. You don't, go somewhere else. So it matters to people. And they have all these surveys that, on mobile, people think it's supposed to be even faster, which is bizarre from the technology perspective. But if you get a slow experience, you go somewhere else, you don't purchase, you don't like the brand, you think the brand is not good. So you need speed. Now, so this is a big part of why we started Akamai, was to try to make it faster. And so first we came out with what we call dynamic site delivery, which is caching. A lot of the images on a page, like the banner, are the same for everybody. So you cache it, you store it near the end user, and when they go to the site, bang, it's just right there. So you can make it be faster, except for cellular. Then we worked on our own virtual internet with our own routing protocols, our own communication layer protocols, and that was Dynamic Site Accelerator. So that made banking sites faster. Sites like, where you're buying something online, made them faster, even if you didn't cache. And then most recently, we're now working on putting software on your device, especially your mobile device, through JavaScript, which lasts for the session. And it tells us what type of device you have, what browser you've got, if you're doing video, what video player you've got. Is it cellular? Is it congested? And knowing all that, we can do optimizations like, hey, if you're in a congested cellular network, we'll compress all the images if you're on a small device, that kind of thing. The next step is predicting what page you're going to click on next, getting all the bits we need to make that page, sneaking it onto your device when you're not paying attention. Okay, or when you're reading the last page, we get 95% of the bits on your device in the interim, so that if you do click on that page, we can assemble it on your device for you, not in the cloud, but on your device. Take the 5% we don't have, like confirm the purchase, and then it seems like it's faster. Because we got to do something to get over this cloud tower bottleneck. The cell tower is a huge bottleneck. So this is technology problem again. Yeah.
I assume you don't do the prefetching in countries where people pay for their bandwidth.
Now this is another great challenge, is you got to make deals with the carriers so the user doesn't have to pay, and we have to detect, okay, is the user going to be paying for this or not? And there's something called zero rating in some countries, where the carrier will make a deal with, say, Facebook, to say that Facebook traffic doesn't count against your billing plan for per gigabyte downloaded. Exactly. Well, that's another thing. You only pay if you clicked on it. That's another one. Yep. And
are they willing to consider that?
Oh, all these things are in flight, in discussions, and of course, in this country, it's all in a mess now with net neutrality. Fortunately for us, Akamai was declared not to be a fast lane because fast lanes will be illegal in 30 days. And there's heavy regulation coming, and regulation is always complicated because it's people have no idea about technology legislating these things, and so all sorts of things can happen. But so we're in the business of trying to use technology to make things be faster. Now, we've figured out ways that we can sneak onto your device through JavaScript, take over your caching there, and where we can put this stuff. We'd really like to be resident on your device, which means we live there all the time. We're not just there for the session, because then we could do a lot more. But again, this is technology. So if folks here can figure out how do you get the right stuff there in the right way ahead of time, well, it's very interesting to us, but interesting to the internet to be able to figure that out, because there's a bottleneck that's not going away. But the users want it to be fast. Okay, the third grand challenge, and this is even harder, is security. Nothing is safe out there. Just you look at the headlines every day, you thought you'd seen the worst. How could it get worse? Then the latest thing happens. And it's like, oh my God, you know. In theory, we knew that could happen, but it just is unimaginable that it did. You know, there's all sorts of entities out there. You know, there's a dozen that just start with O, you know, of entities that are attacking, and for all different reasons. They're state-sponsored, politically sponsored, idealism, organized crime. For the heck of it, it's just huge numbers of reasons and zillions of tools. In fact, the best tools are the ones that are designed to protect websites. And the way you check, you know, it was great. You know, Google published all these tools for the IT manager to check is your app and your website safe. Well, you know who used those tools first? The hackers. Went right in, and no, they weren't safe. You know, you get the latest and greatest hack tools that way. It's just chaos. Now, on top of it, all the protocols that we use for security are buggy. This one killed me. How many people know what Heartbleed is? That's great. Okay. So OpenSSL is a framework, pretty much a protocol pretty much everybody uses to secure their web communications, you know, used for HTTPS. And everything is going to HTTPS. Now, open protocols are generally considered to be the best because everybody uses them. You know exactly what the code's doing. Presumably everybody's checked it. It's been publicly vetted. You know, the government didn't create it. Some company working with the government that you don't trust didn't create it. It's the safe thing, and it's well vetted. Everybody uses it. We used it. Okay. Now, about 4 years ago now, the OpenSSL group, the people that make the OpenSSL stuff, published a patch that said, hey, here's how you can tell if an SSL server is awake and responding. What you do is you send it 64 kilobytes and ask for it to send you back the 64 kilobytes. And if it does, then you know it's awake and paying attention because it received your 64 kilobytes and sent them back, like an echo. Okay, well, it turns out the way that the patch worked was it took the 64 kilobytes coming in, allocated memory for 16 kilobytes to store the 64. But then the protocol said, send back 64. Well, it had the first 16, didn't save the other 48 because it only had 16K of memory allocated. So it grabs the next 48K in memory and sends it back. Now, what do you suppose happens to be sitting in that extra 48K when you're starting up an SSL communication? The keys. But, you know, decent chance the keys are sitting right there. So if you want somebody's secret keys that governs all of their secret communications, just run this openly accessible echo, send them all zeros. You get back some zeros and the secret keys. And now you're off on your merry way. Now, this was not hard to discover, but this protocol was being used universally for 3 to 3.5 years before a researcher published the vulnerability. Now, we asked some of our security folks, so we thought, wow, this seems pretty obvious. Wouldn't governments have known this? Wouldn't crime organizations have known this? So we took a few of our engineers and said, look, they didn't know what the vulnerability was. We said, there is a vulnerability in OpenSSL, you know, that allows you to crack it. Figure it out. Took them a half an hour. You know, all you needed to be doing was thinking, hey, there's a vulnerability. That's amazing to me that it was never published. Now, you can imagine that governments are looking for these kinds of things, especially since so many of them, we know that so many are vulnerable. So presumably any government that was paying attention had everybody's secret keys, literally, for 3.5 years. Any organized crime group that's into, you know, cyber exploitation would have known everybody's secret keys. That's a whopper. There were several, actually, just last year. You know, the shell shock. How many people know shell shock? You know, that was a vulnerability that easily allows you to take over anybody's machine, It's been in the code for decades and just exposed last year. And these are the famous ones. Literally now, what's that? Bash, in Bash. Yeah, just go right in, take over. Takes over a machine. And once you take over the machine, whatever's on there is totally compromised. Decades that's been out there. Now again, that one, you can imagine maybe the company engaged way back when, decades ago, maybe was working with some government, and maybe, if you're a conspiracy theorist, that was a backdoor. At the very least, you got to figure some of the governments out there and crime organizations knew. And the stunning thing is, the security researchers that publish these things, if they knew, they didn't publish it. So even the security protocols are have been hopelessly flawed. And right now, below the radar, every month there's some new thing that comes out related to these protocols. Yeah. I think there's people that are vaguely connected to the government world and criminal world that believe they knew. And I think probably those people believe there's other things still that haven't been disclosed. But is there any published evidence? No, I don't think so. I don't think there's anything in the Snowden files, so far that have indicated that. But they do get exploited when they're published. So this is, the exploit was announced for Bash on September 24th, and just on our customers, we see the exploit attempts just ramp up right away. And these are sometimes called zero-day attacks. As soon as it's announced or somebody figures it out, people go and attack on the very first day. And this is an area where we actually work very closely with the security researcher groups that discover these things so that we can get them patched ahead of time. In fact, it's a very sensitive thing because as part of doing that, we have to promise not to tell anybody. Because if we tell people, then they're not going to tell us. And I did have a very difficult conversation with a senior official at DHS. Wanted to know why we didn't tell him, And so I did suggest, well, you probably got some people across the street that maybe knew, Why don't you ask them? I don't know, But it's a hard world, with so many vulnerabilities now. Now, overall, just the number and the scale and the sophistication of attacks is exploding. These are just, this is the chart of how many significant attacks we've seen on just our customers, by year. And it's, we're over 10 significant attacks a day on our customer base. And now the scale is large. The typical attack is tens of gigabits a second of volume. And of course, there's some very nefarious stuff, hidden in that volume. And every day now, we're seeing some customer get hit with 50 to 100 gigs of volume. Now, that is so big, there is nothing they can do to defend against it. They cannot afford to buy the security boxes that are perfectly good boxes, intrusion prevention systems and firewalls. They can't afford to buy them at that scale. They can't afford to get that much pipe into their data center. So if they get hit with this, they're done. They're either taken offline and or they're infected. Now, the good news for us, is we're doing tens of terabits a second already. The last World Cup game was 7,000 gigabits a second, just that game. So for us, it's a drop in the bucket, and that's where scale really, really helps manage this stuff.
Maybe if the DDoSes could be reused to also send out video, then...
It's, in fact, we use the same, in fact, I'll show you in a minute, we use the same server to absorb the DDoS that does distribute the video. And we're using those same pipes, and it's the same reason you want to have your security defense where the pipes are to the homes. That's where all the aggregate capacity is. So the problem you got today is the traditional solutions everybody uses don't work. Devices, you cannot afford the scale you need. And the carriers don't have the capacity either. And when they turn on the filtering, it kills you anyway. Very inefficient. And so that's where let me show you the approach we use to it. So here's again the picture of the orange servers or the Akamai servers, and we put them everywhere we can. And the way it works now is we put our security defenses, that's the red shield there, in all those servers. We do our application firewall filtering out there and the DDoS absorption out there near the end user. And so when users go to a website, they come through us. When the bad guys go to the website, if they follow the domain name through DNS, they come to us. As I speak, we've got dozens of customers under major assault. And that means, in fact, we've got hundreds of our servers are swamped with DOS traffic. Because locally, you can swamp a server. But we direct users to other servers. And the aggregate capacity, it's a fully distributed network, the aggregate capacity is fine. So nobody knows right now that these 24 customers are being under huge assault. Everything is working fine for the website. We do it at the DNS layer, typically. And so we'll set our time to lives on the DNS layer at 20 seconds, typically. And so a user will fail over directly. For a particular server, it's within 1 second. If you can fail over from one server to another within a cluster of servers, that's a 1 second failover. If the whole data center is swamped, it takes 20 seconds on the DNS time to live. So yeah, pretty good. Yeah.
Silly business question. You charge people by sort of how much they use. So does DDoS get charged against the customer?
That's a great question. When we first came out with it, it did. And I remember we had a very interesting discussion with a very high-profile government website, which is basically ground zero for attack traffic. Every group in every country that doesn't like us bombs this site. So we see all the attacks there first. And early on, there was a massive attack against this site, and we defended it. And they were thrilled. Their normal traffic might be a few gigabits a second, and this was hundreds and hundreds of gigs. They were very happy, called up to say, thank you, you've helped the country. Then the bill showed up, and then they called back. That wasn't a good conversation. Their bill went up by a factor of 100. So, in any event, we also defend against attacks that go straight to the IP address that don't follow the domain name, and that has to be done at the routing layer, the BGP layer. So we do both the domain layer and the routing layer, so we'll reroute to our data centers and then send it back through. But we'll get to exactly your question. You can get this massive spike in your traffic, and we bill based on traffic. So now we cover that. And so we just say, we'll absorb the cost of any attack traffic, because that turned out to be better for business.
What kind of attacks do you see are most prevalent? Reflection attacks?
Those are huge for the denial of service. We want big volume reflection attacks. Attacks are huge. Yeah, a lot of that going on. And there's a lot of sophisticated ones. Some of them, like a slow loris attack or something, there's not a lot of volume, but they soak up the CPU by doing something very slowly. And the CPU just sort of hangs around and keeps it open, and you congest some resource on the...
There's a Bernstein hash function, which is well known, and you can just swap the machine by having it hashed to the same entry in a hash table.
Yeah. And one of the ironic things is, as there's more and more security put in place, security is very expensive. Encryption, digital signatures, very expensive. And so the best attack vector, make that happen a lot. And that swamps out the CPU. So like secure DNS, we've been debating that in the various standards bodies for probably 25 plus years now. Never really did anything. It's good in some ways, but that becomes the attack vector. It's because you require the digital signature, and that swamps out the CPU. So it's very complicated. Yeah?
So this whole ecosystem here, how do you convince people that you're not the mafia, right? That I'll protect you against these guys who can come and scratch your car if you pay me some money. I mean, I'm not saying that you are.
Yeah. Sometimes customers do joke, because it does, when there's these big attacks, it does help our business, because the rest of that industry gets panicked. It'll happen to them. And of course, the entity being attacked, they'll call up, and it's an emergency integration of our services to get them back online. And they do joke, are you sure you don't fund, those bad guys? But no, we don't obviously do that. And, and we have to be careful. One time we hired somebody that we found out later, had a record of being involved, with those groups, and, we had to let them go. So obviously can't be tied to those groups. Yeah.
Slightly different related question. If you're covering the cost, then you have an incentive to also have a non-computing workforce that goes out and tries to prevent attacks in other ways, right?
Well,
The Akamai army that basically gets deployed to shut down rogues in various forms.
that's hopeless. We work with the governments. We send them all the malicious IP addresses. We work with the carriers. Nothing happens there. And the foreign governments, some major foreign governments are complicit. They're instigating this or funding this. It's a very complicated government landscape here.
Notifying them might be the worst thing to do. Because they're like, that was we found. We need to move to another one.
Yeah, no, it's a mess. But this is a huge technology problem, right? As we're working on it from scale, and we see the new attacks every day. We put defenses in place. But there's a lot of technology needs to be done here because we're fighting a losing battle ultimately. It's because there's all these vulnerabilities, and the bad guys, are putting a ton of money into it. Okay, so then the last, yeah.
Just a second. You're saying fighting a losing battle, but I mean, RSA isn't getting slower, and the processors are. Aren't there some things in your favor here? If you're saying that they're able to slow down the CPUs, and that's a significant part of the attack, that seems to be getting mitigated.
CPUs are getting stronger. RSA and any of the encryption algorithms, because of the advances of the people cracking them, keys are much longer. So
Not at the same rate, I would think. I don't know. Can you tell me?
Ooh, I don't know. I do know that we're putting a lot more money into encryption, special encryption devices than we were before. Now, that's not a theorem that says that the complexity of doing the encryption is growing faster than the CPU capability per se, but I don't know.
I'm just wondering if there's some hope that it's a winning game in the end.
There's a lot of work to do. Everything right now is vulnerable. No, the bad guys use your CPU. They use yours. They amass these bot armies, and it's not the breaking the keys. They steal your key. They don't break your key. Now, these crime organizations, there's some government agencies probably work on breaking the keys. They steal it because there's some other loophole, like in Heartbleed, right? Or they get in and...
My point is that if I double the length of my key, they will still steal it.
Yes, they'll still steal it, but it's harder for them to crack it. And we also you have to worry about the cracking because everybody worries about, ever since Snowden, everybody worries about NSA, right? Cracking. And so the encryption protocols are getting much more sophisticated and more complicated.
So is your point that if the key is short, they'll go after it by cracking it, so you have to make the key long to get them to another route, and then
Right.
they're going to, But you can't make the key shorter because then they'll just go right back.
Yeah, and the entities that are doing the cracking, that's more like an NSA probably. The entities that are doing the stealing, that's everybody, out there doing that.
So you talked about custom hardware. Is this like ASIC type things?
Yeah, special purpose, Okay, so that's a whopper, and I'm sure there's a lot of folks here working on algorithms and cryptography. There's a lot of potential contribution for work there, to make this problem better. Okay, the next problem is company networks, and there's actually more money put here than there is with websites, in terms of the business world. And in the old model of the business world, in today's model, I'm saying old already, but it's today's model, is you have an enterprise data center, and then you have branch networks all around the world, and the branch networks connect to the enterprise data center, and that becomes the hub or the gateway out to the rest of the world, the internet. So everything comes called the hub and spoke model. Everything comes back to the core data center. It's not very efficient now that the enterprise employee needs to get out to the cloud for their software as a service apps. They need to go to the internet to do their jobs. Maybe they want to watch a video on the internet. And so you go all the way back to the corporate data center and then out into the internet. You might cross an ocean twice. And that corporate network is hugely expensive. The WAN is very expensive, 10x, maybe 100x what the internet pipe costs. Now, what's happening today is you need 10x or 100x more capacity to connect to the branch office. You don't have this problem in universities typically, but you do in most companies. Because now you want to do video, you want to do PowerPoints. Literally, we're now, we have an enterprise, we have 60 offices. there are times now when I'll get my PowerPoint video on a physical stick. Because wherever I am, I can't get it over the corporate network. All right? And that's crazy, right? We just should be connecting to the internet and sending it that way. Yeah.
I'm sorry, I didn't quite understand the problem yet. So you're talking about like leased lines? What?
Yes, you have a dedicated line. You have MPLS is the typical way.
Sure. So, but why even do that? Why not just use cryptography and do it over the internet then?
That's great. Now you're changing the business world, right? There is $20 billion a year spent where the carriers are selling to the enterprise IT manager your safe, secure, private network. That internet, very untrustworthy. No quality of service. And just read the headlines,
And MPLS sounds like a good acronym.
Yeah. All right, but, it's dying though now. I mean, it's 20 billion and growing, but you need 10 or 100x the capacity, and you can't spend 10 or 100x the cost. And so it's choking. All right, and so of course, our approach to this is to go straight to the internet, and we want to get our software, our servers in the branch offices, in the enterprise data centers, and do in the enterprise networks what we do in the internet, and connect it. And that's a business challenge and an engineering challenge because the carriers, they don't like that idea, because that's like a $20 billion industry to protect and grow. They know there's a need for 10x more bandwidth, and they'd like that to be a $200 billion industry, right? So new technology that upends it is very scary and complicated.
To what extent are standards playing an important role in this area? International standards like ITU and IETF, that kind of thing.
They don't. Because there's so much disagreement. The governments all argue internationally over who's in charge. Even if you just took IETF or folks here, they'll disagree. Look at DNSSEC. We've discussed that for 25 years. And now it's to the point where, it's 25 years old. It doesn't work in the face of the attacks we see today. BGPSEC didn't even get close, right? So BGP is still totally insecure as a protocol. I can spoof anybody's address and steal anybody's traffic. So they're not, playing a role today, I would say, in what's really happening. It's hard. It's all these different entities. So I think industry has a role to play where industry, you can create companies like Akamai that sit on top of that and build our own system as we would like to have it. Academics has a huge role with technology innovation, saying, folks, here is a great way to do some piece of this puzzle, and then get a company to implement it or create a company to implement it.
Software-defined networks, they're playing a role here?
Yeah, everything is going to move to software-defined networks. And I think that hurts the box companies, because it marginalizes what they do. There's NFV, network function virtualization. Probably that's coming as well. So it'll all become software. A lot of the differentiated hardware where a lot of money is all going to become software, I think. And again, that's a great opportunity, for innovation, because coming out of academics, software is a lot easier as a business than hardware is.
How robust is your CDN model against malicious or inept BGP? For example, Pakistan making YouTube.
Yeah, so we deal with that quite a bit. So we monitor all those routes. We can't stop them from doing stuff. We can detect it and try to deal with it as best we can. So we, if Turkey shuts down Facebook, we're delivering it. We can deliver it from outside Turkey. They can then try to filter further. China is a really hard place, right? You have the Great Firewall, and then inside the country, the pipes. They got very sophisticated filtering capabilities. Very hard there. But governments do have the authority to do what they want in their country, and then they're using their technology against the technology of the people on the outside. Some governments are very sophisticated at the technology. So probably got to wind up here, but our goal is to solve these problems. We need help from you to do it, either just straight in academics or, we're hiring, people that want to work on these challenges. And our goal is to make the internet be fast, reliable, and secure. And I think I probably used my time, so I'm going to stop there. And I guess we do questions or something.